All right, folks. Yay, welcome back. Test is over. I hope it was okay. And we're moving on. So last time we went over the first section, which introduced us to functions of several variables. Now we are starting to do calculus. In chapter 4, we'll do limits, continuity, and then derivatives, which for if you have a function of more than one variable, we have to adjust the way we think of derivatives. So we'll introduce these things called partial derivatives, and then we'll get deep into more derivatives of how these things are going to apply to surfaces and things like that. So that would be another day. But today we're going to talk about limits and continuity. And generally, with the idea about limits and continuity, there's two ways to approach this. So the more mathematical way to approach this is to introduce ourselves to epsilons and deltas. I don't know if that sounds familiar to anybody. I'll try to do a little tangent. A little tangent onto a two-dimensional version of that, because trying to do things in 3D, well, maybe I'll draw that 3D picture as well. But in terms of limits, more importantly, in this particular class and in this particular section, there are strange things that can happen with limits when we look at them in the context of surfaces. We do not have a L'Hopital's rule type thing, unfortunately. And so we're just going to get to the limits portion of this by studying, limits in general and applying their properties, and then look at these strange pictures of when limits do not exist. That is, I think, the more interesting problem in this particular section. And then we'll talk about continuity as it relates to limits and functions existing in domains and stuff like that. So that's what we have. All right. The formal definition of a limit. So f is a function of two variables, and b is going to be the domain of this function. And then we want to include things that are near a specific input point a, b. Now, we say arbitrarily close to say that the function does not have to be defined at a, b for the limit to exist. I mean, most of the time when we look at things, it does, but there's going to be some special situations where it might not. And in those cases, well, limit can still exist, but there might be a hole in it. So we've seen that scenario before where you have a graph with a hole in it, and so the limit exists, but the limit is not defined, and so it's not continuous. Now, this statement over here is the pure mathematical way of stating or proving that a limit exists. And
you record?
Yes, it's recording. I'm recording, right?
Okay.
Yeah. And I'll draw a picture of this, but I think it might be better to take a quick look at how this would look like in 2 dimensions. By 2 dimensions, I mean y is equal to f of x functions. So I'm going to just quickly, what should we call this? Diversion. Let's call it a tangent. No, that's so lame. Like that's our favorite calculus teacher joke. Let's go on a tangent about limits. All right, so we say limit as x approaches a of f of x equals L. Just put words here. So we write this limit as x approaches a of f of x equal to L, and we say the formal definition is for all epsilon bigger than 0, there is a delta. Kind of understood that it's bigger than 0, but generally we want to write bigger than 0, such that if you're fairly close to the point A, so a way of saying that fairly close to the point A is saying like the magnitude of x is your like point that's near A, x minus A is less than delta. Oops, sorry. And sometimes we squeeze in we want to allow the possibility that that the function doesn't exist at A. Then putting that point x into the function will get you close, sorry, will get you close to the limit. Okay, so these are a bunch of words that may or may not make sense. Half of it is Greek. Well, not half, but there's a lot of Greek in there. I don't know if that's where the phrase comes from. It's all Greek to me.
You go. I'm trying to follow along.
Yes. This is quite difficult. I think if just hold on to your thoughts and ideas, and if you have any questions, feel free to ask. But I think when we draw this picture, this idea of these words might make a little bit more sense. So let's say that A is here, and let's say you have a graph that looks like that, and I'll put a hole there, a hole, no hole, it doesn't matter, but we're saying that this is going to be your L.
Okay.
All right, so the idea is that you're trying to show me that this limit exists, so I'm going to give you an epsilon. Usually I give you a small epsilon, so you got to work with a small epsilon, and so the epsilon is going to be some distance away, and I can make this as small as possible, as small as I want. Your task is to find me a delta. So your task is to find me a delta where, can I find a delta that's small enough so that if I pick any point, any and every single point within delta of A, so these x values over here would be some randomly chosen x value that's going to be a distance no more than delta away from A, and that if you put that into the function, that's the f of x part, then you're going to be able to capture the value within the epsilon that I gave you. Okay, so I say, okay, I gave you an epsilon, you're able to capture the value. What if I give you a smaller epsilon? Are you still going to be able to capture a value? And then you're going to say, okay, I'm going to pick a smaller delta then, so that anything in here within delta is going to be within epsilon of that value. So that's the idea of a limit existing. Now, let's think about when a limit doesn't exist. And there's several ways for the limit to not exist, but I'm going to pick one way of a limit that does not exist by looking at a graph that has a jump. And then you, as somebody who's trying to show that the limit exists, will have to find an L an appropriate L. So you think, okay, this is shaded in over here, so maybe I'll choose my L to be this L. And then I'm going to give you an epsilon. Say, okay, I'll give you an epsilon. Maybe I'll let the epsilon be super big. If I let the epsilon be super big, then you could choose a delta that is of any size near A, where if I pick any point over here, it's still going to be within epsilon of your limit, right? But if I give you a smaller epsilon, if I give you an epsilon that's small, then you are trying to find a delta. Can I find a delta that's going to be small enough so that every single point that I put in to the function will still be within epsilon? And the answer in this scenario now is no, because if I put in a point over here, then I don't make it to the epsilon portion of things, right? No matter how small my delta is, I'm always going to have this portion of the graph, always going to have this portion on the graph on the left side where it's never going to make it within the epsilon that I chose.
Okay, so.
Okay?
Okay, so that, okay, can you move up the graph? Okay, so the graph that has the 2 points not connecting, that will be the.
Limit exists here.
Okay, that's.
In this example, limit does not exist because if I let my epsilon small enough, then you're not going to be able to find a delta that's going to encompass every single point in there. So usually when math and physics people talk about epsilons, they mean a really small number. And that's generally what happens here. You want epsilon small enough, and then you can find me a delta. So now, just for fun, this is already fun, right? When I was taking these classes where we had to do epsilon delta proofs, we have to write these things kind of quickly, and then we all understood shorthand for these things. I don't know if you've ever taken philosophy and there's like semantics or something like that where you can shorthand a lot of these logic statements, and math is just a whole bunch of logic statements.
Okay, limit does not exist if epsilon is small.
If it's too small that you can't find a delta, that's the point, is that you have to be able to find a delta.
Small and can't find the.
All right. Upside down A stands for all. Have you guys ever seen that?
For all?
Yeah.
Upside down A is for.
Oh wait, there's more. For all epsilon bigger than 0. And another, oh, I forgot what that word is called. There's for all and there exist are 2 like prefaces in logic statements that's covered in like philosophy and math classes. There exists is a backwards E. That's a symbol for there exist. You've seen that? Oh, in discrete math. Okay. There exists delta bigger than 0. And just because we're using symbols such that can be written in this weird backwards epsilon with the 2 dots, such that 0 less than x, less than 0 less than x minus a less than d implies, so the if-then statement sometimes can be replaced with the imply statement, which is a right arrow. F of x minus epsilon, f of x, I keep saying minus epsilon, minus L is less than epsilon. So just for fun, this is a sentence that any mathematician would be able to look at and understand. And there's not a single word in there. Anyways, so that was like a 10-minute tangent. Let's go back to this. And I don't know if it's worth drawing, because we're going to see a bunch more pictures of things that make a little bit more sense than this. But I'm going to attempt to draw it anyways. This is happening in 3 dimensions now. And in our tangent example, it's just y is equal to f of x. So your input is just the real number, x, and then you have a little bit to the left and a little bit to the right of x can be expressed with an absolute value symbol. This here is not the same absolute value symbol that we kind of have seen before, but this actually corresponds to an absolute value. Wait, an absolute value of a vector, does that make sense? It does, right? What do we call that? Magnitude. So what we're really saying here is the magnitude between x, y, your random arbitrary point, and the point in question, a, b, and that's the magnitude. Furthermore, if we look at the square root symbol, let's say you have a surface that looks like this. By the way, this is going to be the surface that I'm going to draw all the time when I need a surface. It's going to look a little bit like an umbrella kind of surface. So the surface has a matching potential limit that we have. Kind of like this drawing over here, you have A, and then you have your limit that is based on, you know, the Y value. So that's what's happening here. And then what they're saying here is that if I give you an epsilon bigger than 0, positive number epsilon, so you go a little bit above, a little bit below your limit, potential limit, that you can find me a delta. Now the delta in this case is going to be a radius of some circle. I guess that's what I wanted to say here. This inequality, the square root of a minus x quantity squared plus y minus b quantity squared, is a circle centered around AB with radius delta. So if I pick you have to find me a delta that's going to be the radius of some circular region, so that every single point within this circle, when you put it up to the function, that you're going to be within epsilon of the limit. All right. So this drawing corresponds, colors and all, I think. I didn't use any blue, huh? I should probably use blue for limit or something. Anyways, this picture, colors and all, should correspond to this picture here, where we talk about a delta distance. You can think about delta here as some radial distance from A, just like you can think about delta here as the radius of a circle within AB. So if you can make those analogies between our y is equal to f of x functions in 2 dimensions versus these functions in 3D, then that's great. If not, don't worry about it. This is all for fun. I'm not going to test you on it, in other words.
Yeah, that's good to know.
Yeah, it's good.
I don't, the first time I take my exam, I don't know what to do. I just feel panicked. Like,
That's why you get 2 chances.
yeah, okay. But anyways, I now know what to do. Just to review some concepts and formulas.
Yes.
And not write a whole sentence
Yes.
about every section.
All right. So the idea of showing a definition exists with epsilon deltas is quite difficult. In fact, there's, I don't know if you guys watch those videos. There's, I think it's Professor Green was doing a video and was showing that the limit exists. And he didn't actually show that the limit exists, but he just kind of assumed because he did so much work already. So showing that the limit exists with epsilon delta can be quite difficult. So what we want to do is we want to be able to rely on limit laws to show that a limit of a constant, limit of x, limit of y as the simplest types of functions are just going to be putting the values in for a and b, or for x and y. So putting a in for x and b in for y will give you the limit, as we've done before when we were doing limits in regular calculus. Only times we would have issues with limits is that when we have an indeterminate form, 0 over 0 or something like that. In which case we had a tool, we had L'Hopital's rule to be able to help us find those limits. Unfortunately, like I mentioned before, we don't have L'Hopital's rule for this. So we're going to, at least for starters, get to use limit laws. And these limit laws really just allow us to put in the values for x and y. Now, if you put the values for x and y and you don't get a 0 over 0 or anything weird like that, then that's great. That's your answer. But if you do put in the values for x and y and you get a 0 over 0, then we have to try to do something else.
Can you scroll up a little bit?
Up?
No, down.
Down.
Down a little more. Perfect.
All right, so limit of a constant is just going to be the constant. Limit of x is just going to be a. Limit of b is just going to be b. Now, assuming we know the limits of f and g as x, y approaches to ab, then the limit of the sum and difference is equal to the sum and difference of the limits. Limit of a constant times a function is the constant times the limit of the function. Limit of a product is the product of the limits. It's not the product rule. We're not taking derivatives here. We're just putting in values and getting limits. So this is just a straight up, the limit of the product of 2 functions is the product of the limit of those 2 functions. Same with a quotient, so long as the denominator is not equal to 0. Power and roots also work the same way. There's some special instances of what happens with the roots, whether the root is positive or whether the root is odd or even. And I use the symbol again for all. Upside down A, remember, stands for all. So for all L, for all limits. And again, all this is going to allow us to just put in the values for our limits, as we'll see in our first example. Okay. All right. Our first example is this. Limit as xy approaches to negative 5, 2 of y squared divided by x squared plus y to the fourth.
Give me one. I'm trying to catch up.
So the quotient here tells us that we can just take the limit of the top and limit of the bottom. The sum and difference tells us the bottom is just the sum and difference of the limit, some power rules. So I'm not going to dig through all the step-by-step uses of the properties, but instead I'll just put in the values. As long as I'm not going to get 0 over 0 or anything weird like that, it's all fair game to just put in the values of x and y. So as x is minus 5 and y is positive 2, then this is all there is to doing limits.
Yeah.
So 4, this is 25, 2 times 2 times 2, 16. And this is 30, 41. All right, nothing to it. You're thinking, why did we have to go through all that epsilon delta when this is all you have to do? Well, that's because I wanted to go over epsilon deltas for fun. But no, we're gonna take a look at some other weird stuff that could happen with limits. Ready? All right. When limits fail to exist, the word fail is kind of a scary thing to see right after the midterm, right? Sorry. When limits don't exist. So back in Calc 1, there's several reasons for a limit to not exist. One of the things that we did over here is that if it comes from one side, it comes from the other side, and they don't match, they don't exist. Right? So one-sided limits are not equal, then the limits way back when we were doing this in Calc 1, we can say that the limit doesn't exist. So equivalently, we can show that the limit doesn't exist if we can find two different ways to get to that point where it's going to give us two different answers. And if that happens, then the limit's not going to exist. So the difference is, back in Calc 1, we have a straight line. We have a one-dimensional domain, right? That's just your x. And then you can go from the left and to the right, and you'll get to that point. So there's only two possible ways to get to the point. Now, let's take a look at what a domain is for these functions. So this is a function that goes from R2 to R. That's a function of two variables, right? And so your domain is going to have to live somewhere on the XY plane. Now, if your point AB is going to be some random point on the domain, then it's going to be some random point on the XY plane. And now let's take a look at a path to get there. Well, there's a path that's going horizontal and a path that's going vertical. Are there more paths? Are there more paths? Yes. Could be going in a diagonal way, or not even necessarily the regular diagonal, but any sort of linear path going there. Are there more paths? Yes. You can go in many other shapes. You can get to it with a parabolic shape. You can get to it with a cubic shape. You can get to it with a square root shape, a log shape, or whatever. You can get to it essentially an infinite number of ways. So if we just check an infinite number of paths to get there, then we're all set, right? So that is to show when the limit exists, is that we would have to check an infinite number of paths to get to that point. How would you show when the limit doesn't exist? All you need are two paths that give you different answers. Okay? So showing something doesn't exist would require you to find two different paths that give you different answers, to give you different limits. All right, let's see. Let's take a look at this example. And a lot of times these examples or these problems that you'll get are going to be going to 0, 0, because that's just the easiest thing to do. If it's going to another point, then it usually gets a little bit more difficult, and you just shift down to 0, 0, or whatever. But most of the problems that you get will be going to 0. The origin. Okay, so what we'll do is we'll construct a graph that helps us find paths. And we're just looking at the domain, so I'm just going to have an XY plane. And then I'm going to find paths to get to the special point that we're reaching, which is at the origin. And then we'll see what happens. So, a path. Let's do a horizontal path. Let's say, consider this path. And usually, with these things, we get to choose paths that go in multiple directions. So this goes from the left and from the right. And this equation of a line here, I can make it a vector, but I think if I just make it a line, that would work too. What is this line, this x-axis? I don't know if I said that question clearly.
Y equals 0.
Y equals 0 represents the x-axis, and that could be the path that I'm concerned about. Okay, so now I'm going to say it's y is equal to 0, and I'm on this path, and I want to follow this function to that path. So I'm going to take my limit. Now, my y is going to be 0, so I don't really need to put that there. I could initially, just to make it clear, but I'm going to stop doing this pretty soon. So x and y, instead of y, it's already 0. So wherever I see a y, I'm going to go ahead and put 0 in there. And then this is what I have so far, since y was equal to 0. So now I'm going to rewrite the limit. Instead of a limit of two variables going to 0, since y is already equal to 0, I'm just going to say, oh, this is just like a limit as x goes to 0, right? And so we have a numerator of 0 and a denominator of x squared. So some little intricacies with limits. I am not going to put the limit in yet. right? If I put the limit in here, I'm gonna get 0 over 0. So I'm not gonna put the limit in yet. I'm gonna simplify what's in the limit. 0 over anything. Before x goes to 0, 0 over anything is already 0. So then x must equal to 0, or not x, but the limit must equal to 0. So as I approach this point while I'm on the graph, let's pretend I'm on the graph. While I approach this point while I'm on the graph, my limit is going to be 0. All right, let's do another path. Let's go along the y-axis this time. And I think that time is x is equal to 0, right? So limit as 0 comma y approaches 0, 0. I'm going to stop doing that. I think I already said I was going to stop doing that, but I hadn't yet. So this is y to the 4th over 0 to the 4th plus 3y to the 4th. All right.
I'm almost caught up to you guys.
Okay. So as x equals 0 is my limit, I'm going to say, because x is already 0, I can say, okay, let's get rid of that variable and change all the x's into zeros. Now I just have the limit as y approaches 0. So as y approaches 0, and then I'm going to have a y to the 4th over 3y to the 4th. And again, before I take the limit, I can simplify that, right? Y's go away, and I just have 1/3. And now, I have two different limits for two different paths. Two different limits, two different paths, so the limit must not exist.
Hold on. See now.
Cool. Sid says it's cool. Yay. Do you guys think it's cool? Now let's take a look at the picture, because that would be even cooler. Back in my day, we never saw pictures. I mean, the math teachers would just say, oh yeah, it'll look like this. What? Oops, I don't want it here. I want it on my other screen. Sorry, I don't have my screen showing yet, but I'll show it to you once I have the function typed up. Okay, let's take a look at see what's happening. If you look at the graph, you can see there's there's some weird things happening at the origin, right? Oh yeah, you have your 3D glasses too, you can see it. Not that you can see it any better. But there's something weird happening. Let's zoom in a little bit. There's something weird happening here. And what's happening is that as we go along the x-axis, you can draw it?
I'm drawing it, so I'll
Awesome. That's super cool. If anybody could draw this and send it to me, I'd be really, really happy. Yeah. We never had the drawing portion of things. I did learn how to draw a lot of interesting things though. Well, a lot of volume of revolution stuff. We're not doing volumes of revolution in this class. But yeah, some three-dimensional stuff. Oh yeah, I'll be drawing some stuff. Okay, I'll try to match colors. I'm sorry if you have a blue-green color blindness. Appearances blue and green are the same, but those are the colors I'm using right now. So the green path is going along the x-axis. Let's get rid of this junk that I had. The green path is along the x-axis, and if I run through the x-axis, I'm going to see that I'm actually going to be constantly at height 0. And by height, I'm meaning that's going to be the output value. Now, if I'm running along the y-axis, I'm actually up here at a different level, and that level is z is equal to 1/3, to be clear. And so you can see that at this point that I want them to meet, they are at two different places. One is at 0, and then the other one is at 1/3. So because they are to two different places, it's equivalent to that going from left and from the right, you get two different limits. Here, I'm taking one path and another path, and I get two different limits, so the limit cannot exist there. So basically, our conclusion is that the limit does not exist. Okay. I don't know. I want to show you something else, but I don't know if I should. Nice shot, too. Speaking of paths, we're going on another tangent. Speaking of paths, I want to express these paths to see how they actually look like with respect to the graph. Now, for a path,
I think I'm pretty sure, I think you made an error because if you go back to the y equals 0, then it's not like it's not x squared, it's actually x4.
Oh, x to the 4th. Okay, thank you. That could be weird if we look at the notes later and say, hey, where's that x squared come from? Thanks, Max.
Welcome.
All right. In terms of paths, if we take a look at let's say the x-axis path, that's when y is equal to 0, right? So I'm going to go and set y equal to 0. And in terms of a path, we're looking at a space curve here. So when y is equal to 0, I'm going to let my x vary and change. So I'm going to call that my parameter t. And what I'm going to do is I'm going to copy this function and I'm going to replace all the y's with 0 and all the x's.
Wait, hold on. So you're saying so you're saying that when x equals 0, the limit of like is 0 comma y? I just can't read that.
Yes, this is 0 comma y, which is to say that x is actually equal to 0.
Okay. And that equals 0, that's approaching 0 comma 0.
Yep.
Oh. Okay, here.
All right, so in terms of our graph, that's going to be a line segment, and I think I made it green, so I'm going to use primary color green. And if I look at that graph, I can see that I'm always going to have a height of 0. And maybe I don't need to be going all the way to, well, I go from -5 to 5. And then if I draw another space curve to kind of depict what's happening when I go along the y-axis, that's when x is equal to 0 and y is going to be the variable, which I'll call t because I want to write it as a parametric equation. And then I'm going to take my function again, where the y is going to be the variable t and the x is going to be the constant 0. And now this will give me a line that is always above the xy plane. And so if I just take a look at these two lines, I see that those two lines don't meet up at 0, 0, which is what I was interested in happening. So that's when the limits don't exist. Okay. All right. So it could get slightly more complicated because those two paths are nice paths because they make one of the variables disappear. Let's take a look at this example where we tried going from the x-axis like we did before. When y is equal to 0, we'll take the limit as, I'm just gonna skip the y equals 0 business and just say, oh, y is already equal to 0, so I only have an x variable left. And then, so this is 2 times x times 0 over 3x squared plus 0 squared. So limit as x approaches 0 of 2. Oh no, that's just 0 because it's multiplied by, everything is multiplied by 0. So again, before we even take the limit, it already becomes 0. Now let's go along the y-axis when x is equal to 0. So y is going to be your only variable left. 2, 0 times y, 3, 0 squared plus y squared. And this is going to give us 0 before we even take the limit. So at this point, it looks like it might exist, but then we're not really sure that it does. And this is not a proof that exists when we get two different paths to get there. Because remember, there's an infinite number of paths. We don't want to check an infinite number of them, but we want to exhaust enough possibilities to say, hey, there's still a possibility that the limit won't exist. All right, I didn't have this earlier, but here are the two paths that we've checked so far. So now let's try a different path. So one of the other paths that we've mentioned are like lines, right? That are not horizontal or vertical. So let's try to find a simple line like y is equal to x. So if y is equal to x, I can replace one of those with the other variable. It doesn't really matter which one we replace, but let's say we'll replace y with x. So wherever we see a y, we'll put an x in there. So we got 2x, wherever we see a y, we'll put an x in there. The denominator is 3x squared plus y squared, so wherever we see a y, we'll put an x in there. All right, so there's no more y's. We don't need to take the limit with the y, so this could be just the limit as x approaches 0. And then what do we have? We have 2x squared and 3x squared plus x squared. All right. Again, things are happening before we even take the limit, before we put x is equal to 0. We're going to have 2x squared over 4x squared. And so that is going to give us a 1/2, right? 2/4. So now we have a different limit from the other two paths that we took. Interesting, huh? I bet the graph would look interesting too. The graph is 2 times x times y divided by 3 x squared plus y squared. Look at this graph. Kind of looks the same as the other one. It has like a little kink to the paper. If we think about this sheet, this graph, the surface as a sheet of paper, and there's not just a kink, but a break. Now, technically, you don't see a break here, but because this is trying to be as precise as possible, it's the computer are discrete things that are happening. So discretely, not discrete, but discretely, but like whole numbers, zeros and ones, right? When they do fractional things, it's like approximation. So we can make this a little bit finer. Like if I put 50 here, it looks like it's closing in, but that's gonna not allow me to be able to spin this as smoothly because it's re-rendering every time we do that. So I'm gonna keep it at, I think it was 31. Maybe I'll keep it at 40 for now. I can hide the edges and do all that kind of stuff. So we could see that if you run along the x and on the y, you're actually on the surface and you're at height 0. But if you run along the diagonal when x is equal to y, then you're at a different height. And I don't know if this is worth doing, but I'm going to see if I can do it anyways. I'll draw the space curve for one of those when x is equal to 0. So when x is equal to 0, and y is equal to t, I'm going to be at height 0. I think this was the blue graph. So I'm going to be at height 0. You see that's just right along the y-axis. So now I'm going to see what happens with the diagonal. So x and y are the same, but I can't use x and y here, right? Because I have to use a parameter. So I'll put x is t, then y is also the same. It's also t. And now when I see this, I'm gonna put t in for x and t in for y. And then this is purple. I'm gonna see I'm at a different height. Those lines are actually skewed. Now I didn't put in the other graph, but the other graph, oh, why not? Just wasting time anyways. If I put in the other graph, so y is equal to 0. This is green. So if I took a look at these two graphs, these two graphs look like they actually intersect at the origin. What happened? There we go. They actually intersect at the origin, so it looks like the limit might exist there, right? But if I throw in my other graph, then I see that, oh, that's the other graph is not meeting at the origin like the others. That's because the function itself doesn't have that limit. The limit doesn't exist. Okay. All right. Pictures. Those pictures are really super cool. Here's another one that I'm not going to do. I'll give you a summary of it, and maybe I'll do it. What do we do? Y is equal to 0. Limit equals 0. Y equal to 1, or x equal to 0. Sorry. And then y equal to x. Actually, this y is equal to x, if you do it, y equal to x will give you a 0, but you might actually have to use L'Hopital's rule for this. But in any case, this gives you limits that are equal to 0. So all these possibilities that we did in the previous problems will all give you the same limit. But the limit doesn't actually exist because there's a special path to get to the origin where it'll give you a different value. And I wonder what that special path is. I'll let you think about it. I think in the homework, they give you the actual paths, and then you show that you'll have different limits. Here, I'm not going to give you the path. I'll show it to you guys next time, but I'm not going to tell you now. You guys could try to figure it out. Okay. All right. The last bit in this section is the idea of continuity. Now, continuity just means that the limit exists and the function exists, and they all have to be equal to each other. So I'm not expecting you to have memorized it, but if you have it in your notes, if you take a look at the epsilon delta definition of before and compare it to what you're seeing in the screen now, can you point out the difference? Anybody? What's the difference from before? It all looks Greek to me. What? What is the difference between this definition for limits versus this definition for continuity. Yeah,
I really don't think this is right, but you have like minus F, A, B, and then there's an L.
you don't
there's no L.
You don't preface that with, I don't think this is right. It's a guess. Take a guess. And if it's right, it's right. If it's not, it's not.
F of AB exists, but for limits, it doesn't have to exist.
Yeah, so for limits, the limit don't have to exist. And like Charles said, the F of AB here is not the same as here. Because for limits, we're not assuming, I already said, we're not assuming that it exists, right? But for continuity, we better assume that it exists. And if it does exist, then it has to be equal to the limit. So the AB here gets replaced, or the L that used to be here gets replaced with the AB. And that's what the limit is. Again, this epsilon delta is just for fun. You can go to your friends and write that little statement without any words and say, hey, look at this math. It's kind of cool. But in reality in this class, we don't have to worry about epsilon delta proofs. You can Google epsilon delta proofs to see, they'll show you some simple proofs and like y equals f of x, but they usually don't get this deep with functions of several variables. But to attack the idea of continuity, or to try to solve problems in our class that deal with continuity, you generally have to look at a function and say, okay, does the function exist there? It does not exist there, or what's happening? And it's really just based on, you're not going to take any serious limits, or it's just going to be based on the domain. So in this first example, the largest plane where it's continuous, you just say for this, you can put in any value for x and any value for y into the sine function, and it'll work just fine. Okay, so you can say continuous for all real numbers for this first one. Or not real numbers. The domain is R2, so continuous for all of R2. This next one's a little tricky. You can't have negatives under ln. Actually, you can't have zeros either for the ln. So xy has to be bigger than 0, strictly bigger than. So that would mean that x is bigger than 0 and y is bigger than 0. Or what?
X is less than 0.
They're both negative. So they both have to have the same sign. Now, sometimes writing it like this would be fine, but sometimes it would actually be better to describe your domain, or in this case, we're studying continuity, where it's continuous. So when they say find the largest region on the xy plane where it's continuous, what would you say? Well, it's these two things, right? How would you describe it using the xy plane? What's this? Say it. Close. You can't have. Yeah. Which quadrant? X and Y are both positive in the first quadrant. X and Y are both negative in the third quadrant. And so this would be the places where it would be continuous. It actually is a domain as well. All right. Okay, so I think we hit all the objectives for this section. Next time, we're going to dive into derivatives. Yay!
Well, okay, so yeah, but you sort of skip, we sort of skip the.
Bye, Sid. Thank you.
Interior points.
Yeah. Well, no, don't worry about the interior points.
Thanks.
All
Bye,
right,
Professor. Thank you.
good seeing you, Ilya. Hope you feel better.
Thank you, Professor. It was great to see you again as well.
All right. So Sam, this is what we're seeing.
I know. I was.
Do you see? Like what I'm seeing at least.
Is that how you see us?
Yeah. Also on my screen on the side. Oh wait, did I stop recording? Hi, Peter.